All right, welcome back, everybody. Sorry about missing Monday. I have a little back issue, but I'm standing and doing much better. So I should be back in action here from today on out, hopefully. I want to go over the midterm, kind of correct a few issues that the exam had, let you know how I graded it, and also get you going on this week's project. Or at least this week's thought process. And from there, we will wrap this term with a project, hopefully. So typically what we've done in this class is done a Revit project, but since we're online and you don't have access to that software, we're not going to be able to do it, but I'm gonna show you it and also demo it so you at least get to see it. It has an energy analysis calculator in it. So Revit is a Autodesk product, kind of like AutoCAD, but a completely different system, a three-dimensional architectural construction system, and it allows you to do energy modeling of a structure. So it's really cool. And usually you get your hands on it. I'll try to get your hands on it through other classes that you take. So you'll get it at some point, but not in this class because we're completely online and I'm not going to make you download that software, which I don't think we have a free license for. So, all right, that'll be later. For today, I want to go through the midterm, which is right here, and also talk about kind of food sustainability. So, all right, I'm going to minimize myself and we can just focus on the midterm. All right, the first one, pretty simple. And I know you had access to the your computer and to Google and everything else. So you could look stuff up if you needed to, and hopefully you did that. Electricity travels down a wire basically by electron vibration. So electricity itself, the energy travels from electron to electron and they're vibrating. They basically bounce each other and it travels down the wire that way. So nothing physically is moving except for energy, which is pretty cool. That's how it moves so fast. It just bumps. One electron bumps into the next one, bumps into the next one, but that is happening so fast that it travels quite fast. So something about electrons here. Vibrating back and forth, make it travel down the wire. Okay. All right, the next one. If a solar array had an area of 300 square feet, with 100% efficient panels, how much energy be captured in 1 hour? So I was hoping you'd look up the constant that we talked about, how much energy comes to our surface. In the back, I did give you some data, so you wouldn't have to look everything up, but I did screw up the unit on that, which some of you pointed out, which I thought was great. So the solar constant is 1 kilowatt per meter squared, not per meter cubed. So sorry about that. But then on the next problem, so that doesn't really help us because it's meters squared and I gave you feet squared. So at this point, we should be able to see units and understand, oh, this is different. I did do the conversion for you in the next problem, which again, didn't really help you. I should have had it for you on this problem. 0.03 kilowatts per foot squared. So if we do know that, right? Now that does help us. So, and we say we have 100% efficient panels. We know this much comes per foot squared. And so we should be able to figure this out. How much energy could be captured in an hour of sun? So in an hour of sun, right, we get essentially this much information, this much per foot squared. So all we need to do is take our 300 square feet and multiply it and do our unit cancellation, and we're left with kilowatts. So 0.03 of 300 should be something like 9 kilowatts. So that's in 1 hour. That's how much comes. If we were 100%, capturing that, this is a lot of energy, a whole bunch of energy. So you should kind of know by now about, how much that is. And that's in just you know, 300 square feet of panel work. So, and 1 hour. So you're going to get multiple hours per day if you're in a sun area, and then you're going to get it, you know, over a 30-day period. So that's a lot of energy. All right. Then the next one also had, again, some unit problems. Just so you know, I have corrected that now. So the poor next students won't have what you had, but I'm going to adjust this when I grade it. So that's why I go through this first before I do the grading. But it says given a load of 10 kW per month. So remember, load is like the energy, the house use, right? 10 kW per month. How many solar panels would it take to produce this amount of energy? So we're looking for 10 kW. Right? And we know that the solar constant is 1 kW per meter squared, and or the 0.3 kilowatts per foot square. The panel rating is 300 watts. So we get 300 watts, right, per hour. That's how panel ratings are of direct sunlight. And we get 2 hours of sun per day, right? So that means that we're getting 600 watts per hour, or per 2 hours, right? But we're getting 600 watts per panel. How about that? Per panel in this location. And we got to get to 10 kW. So, and the 10 kW is per month. So I do say that there's 30 days. So we should be able to take this 600, multiply by the 30, and see how much, you know, one panel is going to produce. So it looks like it's going to come up with 18,000 watts, which is 18 kilowatts per month. Is how much that panel, this 300 watt panel, 300 watt panel is pretty good sized panel. It's big. But that's, you know, if we get all of those sunny days and we don't have any reason to reduce this, I didn't give you a solar day count or anything. I just said 30 days. So this one panel is clearly going to produce enough for this 10 kilowatts. It's going to produce 18 kilowatts, right? Because it gets 2 hours a day times the 30 days. So I didn't mean for this to be any more complicated than that. This should just say one panel. All right, let's keep going. 2 advantages of solar energy and 2 disadvantages. So there's a lot of advantages to solar energy. It is fairly inexpensive compared to other systems out there. So you could have cost as part of it. I like the no moving parts. I also like the fact that the energy is collected near the source or near the load. So, you know, we don't have to, you know, use a wave buoy that's 30 miles offshore and then get that energy to shore. Solar is collected on spot, right? So, you know, cost, location of the collection compared to the load, no moving parts, a fairly simple system to use and put together compared to some of the other more complicated ones, like a giant wind turbine or a, you know, a geothermal system that requires drilling and big equipment and, you know, on and on and on. So hopefully you came up with 2 solid. We got cost, we got location compared to ION compared to load. Right, those are all very big advantages. Availability, it's available to everyone if you have sun, where hydro's not, right, or geothermal's not. Yeah, all right, so then disadvantages clearly would be the lack of sun or the night. So it's definitely a cyclical production, right? where hydro could be continuous if you had water flowing. And wave is actually fairly continuous. There are very, very few days on our coast that don't have some form of wave action. So solar night is a problem for sure. Efficiency. You know, they're still just not very efficient. We're not capturing that much energy where there's a whole bunch more available. And then of course, storage is always a problem. So yeah, I'll look at what you got. All right, so given a solar angle of 72 degrees, so it didn't, again, not looking to make this any more complicated. 72 degrees solar angle, what angle would we put our panel at? And we want our panel perpendicular to that 72. So if I draw a perpendicular, and I know that's 90, right? And I know this is 90, and I know that right there is 72 degrees, right? So this would be the angle typically that we would want to reference. From horizontal, what angle do we want to put our panel at? And to do that simple math, we know that the interior angles are 180, right? Interior angles 180 of a triangle. So we have a 72, 90, add those together and then subtract it from 180. So 18 degrees on this one. So 72, I didn't draw a very accurate, 72 is like here. So then perpendicular is like here, and 18 degrees is what we needed for our panel angle from horizontal. That's what you would tell the text to do. That would be a Somerset because that sun is so high up in the air. Okay. All right. Sustainability for companies. Again, says give me 3 topics and examples. It's pretty easy to come up with these. You know, a lot of times, unfortunately, one of the primary reasons companies use sustainability is for marketing to try and sell products. A better reason would be just for the environment. And then, of course, under that, you can list a lot of things like water, air, soil, you know, all of those things are things we're trying to conserve and keep clean. So sustainability does a lot with, you know, waste. That's another area. Trying to reduce their waste and save cost. Trying to save the environment, not heat water up, not pollute air, not pollute the soil, all of those kind of things. So, you know, you should have been able to come up with this, hopefully no problem. There's lots of good reasons for companies to do it. These I'm really sorry about. Looking back at your exam, there's like these extra boxes, and that's where I actually hid the answers. But when it printed, it put the boxes in. So, I mean, I'm so sorry about that. So I'm going to grade these really easily. But this is what you got. And this is what you should have got. Really understand quite how it did it. It's like the Adobe system did this to me, where you have all these weird extra boxes, right? Well, that's where the answers are, right here and here. So yeah, I'm just going to look at your effort on this and really go easy on it. This is what you should have had. Bad. This one, turbine. This is a hydro system, so it's got to have some kind of a turbine, and this is one of the water jets that we did talk about. What else do we have? Okay, so then energy comes from the turbine and typically goes into a controller. So that energy's got to be dealt with. It needs to be sent to the battery, something like that, some kind of a storage system, if there is a storage system. And that usually has some kind of disconnect. Right, and that's so you can work on that system. But you know, this would be some kind of a storage A lot of times it's a battery. Okay. And then the controller also sends energy to the home or the load. And that also goes through some kind of a breaker. And you could call this a breaker too, right? Those are just disconnects. And that's so the home can be worked on. This is like the breaker panel in your house and kind of thing. Now, if we're going to use it straight into the house, then there would be an inverter too somewhere to convert that. So this could be an inverter. And then the breaker panels inside the house somewhere. So I'll take any and all of that. Basic components though, hopefully you got those in there somewhere. Sorry about the horrible graphics. All right, I'm not sure I spent a lot of time on this, but it's good for you to kind of know how a panel works. And again, it should have looked like this. And I think, I don't know, this is what you got. Some crazy boxes that I'm sure were super confusing. So I'm really sorry about that. But I'm going to go through it anyway, because you'll get something like this on the final and it'll be clear, I promise. A solar panel typically, and it did say solar panel, it's an array of solar cells. So these are cells. Right? So 1, 2, 3, 4, lots of cells typically in a solar panel. Okay. And then the parts of that panel are going to have a positive. So that's a silicone material that has a positive tendency to it. All right. And then it'll have also a negative. And that's this here, the bottom. A negative tendency to the bottom material. So you have a positive tendency and a negative tendency that they're not connecting to each other, right? They're not activated until the sun hits them. But when the sun does hit them, comes in and hits these little negatives, they'll jump to the positive, and that jump creates electricity. So in between, there's got to be some kind of a conductor. Some kind of a material that allows them to conduct and travel back and forth. Okay. So again, remember, electricity flow is just this vibration thing. Once we get that vibration going with the sunlight, it activates that and we get our negative positive flow. So this would be to the load or the storage, right? This is where we're sending it. Now there was one more arrow in there and I don't even know if you could see it, but this is essentially the framework. So all solar panels are going to have some kind of frame. That can be an aluminum frame. Steel is not good because it's super heavy, but there are some steel framed solar panels out there. So we have cells, we have a positive material, we have a negative material, and then we have a conductor between those two materials. And then usually there's some kind of frame. That's what I was looking for. So again, not the greatest diagram for you, although we have squares. So sorry about that. And that's the end. All right, so I'm going to go through those, grade them up, be easy on the two problems that just kind of got mucked up. We're also going to talk about food sustainability this week. And I'm going to have you watch a video by the indigenous folks on their concept of food sustainability, and I hope that can resonate with you. It should, because we have a food situation in this country and in the world. Our population growth is going faster than our food capability. So at some point, unfortunately, generations in the future, probably not my generation, we're going to have some kind of a food crisis or a food situation. You should be aware of that. And you may be aware of that just based on the COVID situation. Our food supply is about a 3-day food supply. So if our transportation system for some reason did not work or failed, due to COVID or due to any other unimaginable situation in the Portland area, in our area, we have so many bridges that If we ever do get a large earthquake and it takes out the bridges, more than likely you will not be able to drive to a grocery store. Hopefully you live in a populated area where you could walk to one, but that grocery store typically will not be able to receive the food. So on a normal day, we have a 3-day food source if everything is working well. So just imagine if transportation breaks down like it did in COVID, we saw empty food shelves in the grocery store. That was a little startling. So the concept of food sustainability should resonate with you. It should resonate with everybody. And we should think about trying to produce some of our own food. I know if you live in an apartment complex, that's not going to happen. But if you have land at all, or you have land available, sometimes there's community gardens that you can use. It should be something you think about. I'm not saying hoard food or stock up on food, but you might consider some kind of a backup plan. Like, what would your plan be if the supply chain fails for a while? Okay. So, for example, I have a storage of dehydrated food, not crazy amount. I'm not a survivalist, but survivalists have crazy amounts, and that is doable. It's expensive. But we do have, canned foods, and we have some dehydrated foods, and we're ready to eat out of our pantry for a month or two. That's not that difficult to do. You're not going to eat well, but it's not that difficult to do. So it's an interesting time to think about all this and think about where your food source comes from. So if you're shopping locally, hitting farmers markets, that's great. Like, that is helping the food supply situation. The problem is those will get 100% hammered in some kind of crisis. So that won't be there. All right. So it is really a good thing to think about. It's a short video on sustainable food concepts, but it does talk about some good strategies to try to help that situation out. Okay. All right. Take care. And I will talk to you again this week.